In today's lesson, we are going to work on inverses, not only inverse graphs, but we're also going to look at inverse equations. And what we're going to focus on are our parent functions. So y equals x squared, y equals x cubed, y equals 1 over x, and then also the exponential y equals b to the x. We didn't look at a lot with y equals b to the x with transformations, but we're going to really focus on that during the second half of chapter 5. Please keep in mind when we are doing exponential functions, b to the x, there's an infinite number of bases, so we're just going to use base 2 for our example today, but remember it can be any base possible, provided it's greater than 0 and not 1. Okay, so to begin with, we're going to look at the parent function and we're going to compare just different things about these parent functions. Because they are that parent, we're going to be looking at doing some transformations with them, which in turn means we can look at the transformations of the inverses as well. So for the first one, y equals x squared. So we learned the other day that we can either write out the operations or, more specifically, we can just interchange x and y and solve. So therefore, x equals y squared. And now we have to solve for y, get y by itself, so square root both sides. So y equals the positive and negative square root of x. Remember, with the squares, that was one of the special cases. In order to get that parabola, the inverse of it, we have to have both of them. So I'm going to graph the original parent function, the parabola, and then I'm also going to graph its inverse. Feel free to do this and pause it. That way you can see for yourself that you're able to do these. So there's my original y equals x squared, and then I have to do my inverse, so I can either graph each of those, or I could take these coordinate points, flip-flop your x's and y's, whatever makes sense to you to do, does not matter. And we get our sideways parabola. We should notice we have that symmetry piece, so I can draw in there that line y equals x. I'm just putting a dotted line because it's not part of my functions, but I can see that it reflects over that line y equals x. Again, that's just kind of what we've been working on all along. The second one, y equals x cubed. So when I do y equals x cubed, interchange x and y, and then cube root both sides. Please keep in mind with the cube root, there's no positive and negative. The cube root of a negative is a negative. The cube root of a positive is a positive. I get all my same or correct values out with negativity. So I'm going to graph my y equals x cubed, and then I'm going to go through and graph my inverse. Okay, so there's my cube root, obviously not perfect by any means, or my cubic, excuse me. And then when I graph my inverse of that, so this one might be a little harder to see. We haven't worked with this one as much, so I'll talk through it instead of just graphing it on here. So when I look at those points, 0, 0 is still 0, 0, 1, 1 is still 1, 1, 2, 8 is now 8, 2. Negative 1 is still the same, and then negative 2, negative 8 is now negative 8, negative 2. And so I get this kind of rotated or reflected graph. So that is your cube root graph. So you've never done a cube root for a parent function, but that's what the cube root looks like. Cube root looks like this, and then like this, where there's that turning point in the middle there as well. Okay, again, I can draw in that line y equals x, and you should see that symmetry between the two different colors. Okay, next two. Y equals 1 over x and y equals b to the x. These are two special types. Their inverse is a little bit different. So we'll start by working through the first one, y equals 1 over x. So x equals 1 over y. Multiply both sides by y to get y out of the denominator. So now I have y times x equals 1. Divide both sides by x. Y equals 1 over x. Y equals 1 over x, which is the same as the original. This is the inverse. So the inverse is exactly the same thing as the parent function. So now if I go through and I graph that, I do know with the reciprocal function we have those asymptotes. So we have a vertical asymptote at x equals 0. Oops. A horizontal asymptote at y equals 1. And then I can plot some of those points. I know 1, 1. If I put in 2 for x, I get a half out. If I put in a half for x, I get 2 out. And then negatively, negative 1 is negative 1. And then we have those, and we have asymptote behavior. Okay, quick sketches. Okay, so there is my original function. Now, if I draw in that line y equals x, I'll use a different color here so you can see it different than your asymptotes. So technically, I should reflect this onto itself, or over the y equals x line, and what ends up happening is it's the same, because this point here reflects over this line, and that's this point here. It's on itself. So since my original function has symmetry about the line y equals x, my inverse is the same. So just kind of a neat feature. Nothing super spectacular about it and what we're going to continue to work on. It is just something that is good to be able to see. Okay, the last one, which is where we're going to spend most of our time, is that exponential function. So y equals b to the x. Again, we are going to use 2 for our base. So y equals 2 to the x. Okay, so when I go through and I do my inverse, I interchange x and y. Now I have to solve for y. How do I get y down from my exponent? I mean, if this problem was this, that's really easy. How do you get y by itself? You square root both sides, positive, negative, but you square root both sides. But in this case, my exponent's my y. How do I undo a y? There's no y root. So that's going to be the focus for the next couple of lessons is how do we get that y down? Now at this point, we can't. Okay, we don't know how to do it. So therefore, when we graph our original function, when we graph y equals 2 to the x, I can go through and I can make my table. I know we have 0, 1. 2 to the first is 2, so 1, 2. 2 to the second is 4. 2 to the third is 8. I can put negatives in. 2 to the negative first is a half, etc. So we get that exponential function. Again, nothing spectacular that you haven't done before. Drawing that horizontal asymptote. So now, if I want to do my inverse, how do we find the inverse of a function? How do I graph the inverse of a function? Interchange x and y. So this might be a point where you want to make a table so that you can visually see your table. But what I'm just going to do super quickly is I know since there was a horizontal asymptote, there's a horizontal asymptote here at y equals 0. What kind of asymptote happens in my inverse? X equals 0. Remember, x's and y switch. Since my x and y values switch, my asymptotes switch as well. And then I look at all those coordinate points, and then we just have to be really careful. Again, that might be where a table comes in really handy here. So I had the point 0, 1. So that means I now have the point 1, 0. I had the point 2, 4, which means I now have the point 4, 2. I had the point 3, 8. So now I have the point 8, 3. And then over here, I had the point negative 1, 1/2. So now I have a point 1/2, negative 1. And again, I have that asymptote, which helps me with my asymptote behavior. Not perfect by any means. But then I can go through and I can draw in that line y equals x. And I can hopefully see quickly that it looks like it reflects over it. Those two functions do. So we have the original graph and then we have this inverse. And so this purple part here, this is what we're going to be focusing on. That graph has a vertical asymptote. That graph has some special characteristics about it. At this point, I do not know how to write the equation of an exponential's inverse in y equals form. But again, that's what we're going to continue to work through, and we're going to learn how to do. So now, what I want you to do is we're going to pick a different base. We're going to pick a base of 3. And what I want you to do for this, so this is what we're doing, y equals 3 to the x. What I want you to do is I want you to make an xy table for the inverse of y equals 3 to the x. If that means you need to make a table for y equals 3 to the x, that's perfectly fine. The focus here is what's the inverse of it. And then I'm going to have you graph it as well. So pause the video, please, and go ahead and do that. So I wrote the table for y equals 3 to the x, and then I just flip-flopped my x and y, so my x and y's values switched. So now I just have to take this table and go ahead and put it in my graph. Please note, all I'm doing is I'm graphing the inverse. So what I'm going to be graphing over here is x equals 3 to the y. So x equals 3 to the y. Because I just interchanged my x and y. Because this first one here was y equals 3 to the x. So that's here. So the inverse is what I have here. So I'm technically graphing x equals 3 to the y. That is this. So therefore, I'm going to put those points on my graph. Okay, so I get this shape. Now keep in mind, this is the inverse of an exponential. The inverse of an exponential, every single one of them has what graphing characteristic? A vertical asymptote. Good. So we have a vertical asymptote here at x equals 0, and that is what the inverse function looks like. So I already answered this next question here without realizing it. So write the equation for the inverse, even though it's not in y equals form, so that's x equals 3 to the y. Okay, and then the last part is here for D. It says if the input for the inverse, so for this equation, if the input for that inverse is 81, what is the output? So input means x. Okay, so therefore, what must y be? 3 to what power is 81? Perfect. 4. So you'd be able to figure this out. It's the exponent. It's the exponent on 3 to get to 81. So that's what you were trying to figure out. That's what the output value is. So one of the things that's been useful for figuring these pieces out is the following puzzle. So this is kind of just a fun little puzzle to reorganize what we have. And there's this word called logs. And logs are a really big way to help us when we're trying to write the inverse of an exponential. So we have the following situation. So there are 4 clues to help you figure out how this puzzle works. So with these 4 clues, they are all true statements. They're equations. So the way this is stated, so for this bottom one here, this is log base 2 of 8 is or equals 3. So that's how it's stated. So I want you to think about logically, like what does that mean? Okay, and then the second one is log base 5 of 25 equals 2. Okay, why is that true? So I want you to just kind of think through that for a moment and figure out what kind of pattern is happening, what's happening with each of the pieces, is there a way to rewrite, that sort of thing. And then what I want you to do is I want you to pause it and I want you to come up with these 6. Please don't look at my answers or listen to me explaining it until after you've really thought through this. Because logs are one of those things that students sometimes struggle with. So the more you understand what a log is, the better off you'll be. So pause it right now and try to answer these 6 questions looking at the relationships where all of those numbers are located in the log. How else could you represent those? Okay, so if you haven't done this yet, re-pause me. But I'm going to go through how to rewrite these, or how at least to think about these differently. So log base 2 of 8 is 3. So for log base 2 of 8 is 3 for this statement, you know that the 3 is the exponent on the 2. This is the same thing as 2 to the 3rd equals 8. So that 3, what the log equals is the exponent. A log equals an exponent, just plain and simple. By definition, a log is an exponent, equals an exponent. So in the second one, you can rewrite this as 5 squared equals 25. Now, you're not always going to want to rewrite them, nor do you need to, but just think about it. Okay, that's my exponent. So my base is always that subscripted piece, and then my base to my exponent equals this part inside here, which is called the argument. Same thing over here. 3 to the 3rd is 27. And then 10 to the 4th is 10,000. So for all 6 of these, that's what in essence you're doing here, is you are rewriting them. So 2 to what power is 16? That's 4. For B, 2 to what power is 32? That's 5. So now C, I've taken away your base. What squared is 100? Well, that's 10. For D, 5 to the 3rd is what? Oh, 5 to the 3rd is just 125. What to the 4th power is 81? That's 3. And 10 to what power, or sorry, 100 to what power is 10? That's a half. And you can look at it this way. 10 to what power, 100 to what power equals 10? And it's the square root of 10. The square root of 100, which is 10. Man. So we're just starting to look at what logs represent. So what I want you to do is lastly, read the following. And I want you to now put that inverse into y equals form. So if I want the inverse of this, it is x equals 3 to the y. Now, when we go back and we look at what we just finished doing over here, I have this in exponential form. So this here is very similar to the first one, where I had 8 equals 2 cubed. And for 8 equals 2 cubed, that was equivalent to log base 2 of 8 equals 3. So now, to be able to rewrite this, where it's in y equals form, remember a log equals the exponent. So therefore my exponent is what my log equals. So this is log, what's the base of the exponential? 3. The base of the log is the base of the exponential of x equals y, because your exponent is what a logarithm equals. You now just wrote the inverse of an exponential. Congratulations.